So good evening, all of you. In the last class, we discussed about attacking reagents, another reaction mechanism, two types of the attacking reagents, electrophiles and nucleophiles. Next, reaction mechanism. Next is reaction mechanism. What is reaction mechanism? For example, see here, I can express a simple chemical reaction like reactant to product. Reactant to product means here a reactant is converting into product, means the reactant undergoing chemical change to gives product. This is the outline of a chemical reaction. Outline of a chemical reaction. But what happening inside of the chemical reaction? What happening inside of the chemical reaction? Right, see here first. The reactant first is converting into X, then it is converting into Y, and finally transforming into product. This is the original pathway of this chemical reaction. The original pathway of this chemical reaction. For example, this is a first step reaction. This is a second step reaction. And this is a third step reaction. Means here, the reaction mechanism provide a detailed data, a detailed and stepwise description of a pathway, gives detail and stepwise description, first step, second step, third step, stepwise description of the pathway. This is the pathway of the reaction. This is the pathway of the reaction, which is called as the reaction mechanism. Reaction mechanism. Here, what happening in this reaction mechanism? It gives the detailed and stepwise description of this pathway. And this reaction mechanism not only deals with the structural change, See here, initially a reactant, then converting into X. During this, there will be a change in the structure observed. Then here, some change in the chemical structure observed. And finally, our desired product. So it not only deals with the structural change, but also deals with the change in energy. Change in energy, that is in terms of the thermodynamic parameters like Gibbs free energy, enthalpy, like that, right? Okay. Whenever we are going to deal with a particular reaction mechanism, whenever we are going to study about the reaction mechanism, we have to observe the following parameters. Means whenever we are looking into reaction mechanism, we must and should observe the following parameters. What are those following parameters are? Electronic displacement, electronic displacement, electronic displacement. The second one is bond cleavage. The second one is bond cleavage. The third one is types of intermediate, types of intermediate, and last one is type of mechanism. Type of mechanism. These are the observation we have to done while we are studying about a reaction mechanism. While we are studying about a reaction mechanism. See, this type of mechanism, the type of mechanism, which type of mechanism that can be decided by the type of the intermediate. Intermediate, it may be carbocation, it may be carbanion, it may be free radical. So that intermediate provides such a type of a mechanism. What is the intermediate we are getting? It may be the carbocation, it may be the carbanion. That can be decided by the bond cleavage. Maybe homolytic fission, it will give the free radical intermediate. If it is a heterolytic fission, it gives the carbocation free radical as well as the carbocation intermediate as well as the carbanion intermediate. And the bond cleavage depends on the electronic displacement. What is electronic displacement? Displacement of a electronic pair in covalent bond. Displacement of electron pair in a covalent bond, right? So there is a interconnection between one and one. So this depends on this depends on this, and this depends on this. Like that, we have to observe all these conditions while we are studying about a reaction, particular reaction mechanism, right? This is some introduction about the definition of the reaction mechanism. Then, then first, so we discussed four parameters, right? We'll move one by one. The first one is electronic displacement. The first parameter under the reaction mechanism, electronic displacement. What is the electronic displacement? Displacement of electron pair. Displacement of electron pair in a covalent bond. In a covalent bond is called as electronic displacement. Displacement of an electron pair in a covalent bond is called electronic displacement. And these electronic displacement classified into two types. This electronic displacement classified into two types. Right? Okay. Type 1 is permanent electronic displacement. Type 2 is temporary electronic displacement. Permanent electronic displacement, temporary electronic displacement. What is a permanent electronic displacement? The displacement of electron takes place either in presence of reagent, in presence or absence. Displacement of electron in a covalent bond takes place either in presence of reagent or absence of reagent. Means the requirement of reagent is not mandatory. Such type of displacements are called as the permanent electronic displacements. Example, inductive effect, hyperconjugation, resonance effect, which is called as a mesomeric effect, resonance effect. Next, what is a temporary electronic displacement? Means here the displacement of electron pair in a covalent bond takes place only in presence of reagent. only in presence of reagent. Means here the request of reagent is mandatory. If there is no reagent, no temporary electronic displacement. Example of the temporary electronic displacement is electromeric effect. Electromeric effect. Electromeric effect is the example under the temporary electronic displacement. Temporary electronic displacement. Right. Now, first we look into the permanent electronic displacement. We have three types of the permanent electronic displacement. First, about the inductive effect. Inductive effect. Right. Inductive effect. Right. What is an inductive effect? What is an inductive effect? Partial displacement of electron pair. Partial displacement. Partial displacement of sigma electron. Of sigma electron towards more electronegative sigma bond. More electronegative sigma bond is called as inductive effect. Partial displacement of sigma electrons towards more electronegative sigma bond. Once in this inductive effect, the partial displacement of electrons is taking place. Not complete displacement is taking. Partial electronic displacement takes place. Therefore, the respective atoms acquires partial charges. Partial charges. Right? We will discuss with some examples. Right. I can write this. I can write this X. It is a hydrocarbon having a carbon chain, and the terminal group is any X. Condition of the X is here. Condition of this first case is here. The electronegativity of X, electronegativity of X is greater than the electronegativity of carbon. Electronegativity of carbon. So here, more electronegative, less electronegative. Then now what happens here? Displacement of sigma electrons towards more electronegative sigma bond. Among these two, which is more electronegative? X is more electronegative. Therefore, here electrons transferred towards X. Electrons are transferring towards X. So therefore, what happens once X is receiving electrons? Partial displacement. X is receiving electrons. Therefore, here negative charge, that to the partial negative charge appears on X. And once carbon is losing electrons, therefore here the positive charge arises over carbon, that to the partial positive charge on carbon takes place. Right. And one more case is here. One more case is here. Y. Here the case is reverse here. Here the electronegativity of Y is less than electronegativity of carbon. Here Y is less electronegative than carbon. More electronegative, less electronegative. Then what happens here? The electrons are, that means These sigma electrons are displacing or transferring towards the carbon. Once it is receiving electrons, negative charge. Once it is losing electrons, positive charge, and that to the partial charges. Partial charges. Now see here, you can observe these two. In these two cases, always the electrons are transferring towards the more electronegative atom. More electronegative atoms. Right. Here, once X X withdraws electron from the adjacent carbon. X withdraws electrons from the carbon. Therefore, this X is called as electron withdrawing group respective to the carbon. Electron withdrawing group respective to the carbon. In the same way, coming to the case 2 here, the Y donate electrons with respect to the carbon. Therefore, this is called as electron donating group. This is called as the electron donating group because it donates electron. This is electron withdrawing group. This withdraws electron. Electron withdrawing group is indicated with the negative sign, and this is I minus inductive effect. Electron withdrawing groups are classified as minus inductive effect, whereas electron donating groups or electron releasing groups, whatever it may be, so that can be considered as positive inductive effect. Negative inductive effect, electron withdrawing group. Positive inductive effect, electron donating group. In some books, they mention like this E or G. Both are same. Electron donating group, electron releasing group. Right. Okay. Now here see, first we discussed about only one bond, but we have so many bonds left through the main chain, that is depending on the length of the chain. So here the inductive effect travels and decreases through the distance, decreases through the distance. Inductive effect travels through the chain and inductive effect decreases as the distance increases. As the distance increases. Let me explain. Now see here, this is carbon 1, this is carbon 2, and this is carbon 3. X withdraws electron from the carbon 1, therefore the positive charge is developed on the carbon. Once the positive charge is developed means the carbon 1 is electron deficient. Then the carbon automatically withdraws electron from this carbon, withdraws electrons from this carbon 2. This carbon withdraws electron from the carbon 2. Then obviously what happens when the carbon 2 losing electrons to the carbon 1, it becomes electropositive. Becomes electropositive and given as like this. Similarly moves on. Similarly moves on. The positive charge develops on the carbon. But see here, this carbon 1 cannot able to withdraw electrons from C2 as X withdraws electron from the carbon 1. Here, X withdraws more number of electrons to the carbon, but this carbon 1 cannot able to withdraw this much of electrons, which is withdrawing X from C2. Means inductive is more in this case. As we are moving on, the inductive effect decreases. Inductive effect decreases. As the number of torsion, as the number of deltas increases, which indicates decrease in the inductive effect. As the number of the deltas increases, it indicates the decrease in the inductive effect. Right? The inductive effect in a long chain effectively works up to carbon number 3. up to carbon number 3. Later on, that will be negligible. That will be negligible, right? Okay, next. For example, you have a question, right? You have a question. I will give some compound. Now you have to identify which is minus inductive effect and which is plus inductive effect, right? So just now we discussed that in the first case, X is minus inductive effect because that is more electronegative atom. The second case, Y is more electron donating group because that is electropositive, less electronegative based on that. For example, right. This is the example one. If you face such type of question in the examination, part A, part B. I have a molecule one. It is consisting of the two parts A and B. In this options, option A minus inductive effect, B plus inductive effect. Like that, you may have options. Then how will you identify what is the correct answer? Whether A is the plus inductive effect or B is plus inductive effect, vice versa. Then how to identify? Right, see here. In such type of examples, see here all the carbons of the part A are sp3 hybridized. Sorry, sp2 hybridized. sp2 hybridized. 1, 2, 3, 1 hydrogen. 1, 2, 3, sp2. Like that, each carbon of this part A is sp2, whereas the each part of the B is sp3 hybridized. sp3 hybridized. So what? Yeah, but this is not your answer. This is not my answer. I did not ask about the hybridization. What I mentioned, which is the plus inductive effect and which is the minus inductive effect. Right. Electronegativity is directly proportional to percentage of S character. Percentage of S character. As the S character increases, electronegativity increases. In this case, the percentage of S is 33.3. In this case, the percentage of S is 25%. Here, more S character, therefore, more electronegative. Once it is more electronegative, minus inductive effect. Once it is minus inductive effect, it is plus inductive effect. Therefore, A is minus inductive effect, whereas B is plus inductive effect. Right? Okay. Next, I will give with one more example. Same here. I have part A, part B of compound 1, and which belongs to the plus inductive effect, which is the minus inductive effect. Right here. Same here. Same will repeats here. Then we know that 1, 2, 1, 2. This is sp hybridized B. We know that this is already sp2. This is 33.3 and this is 50%. Therefore, electronegative group as usual minus inductive effect, and this is plus inductive effect. So here, based on the hybridization, we can decide whether it is the which is the electron withdrawing group, which is the electron releasing group. Among these two, this is electron withdrawing group. and this is electron releasing group, right? So some more examples. So as electronegativity is directly proportional to S character, as S character increases, electronegativity increases. As electronegativity increases, electron withdrawing property increases. So that we can decide, right? This percentage of S character, the percentage of S character, based on that hybridization, we know that which hybridized molecule is more electronegative? Sp, sp2, sp3. The molecule with sp hybridized is more electronegative follows. Then second one, bond angle. Second one, bond angle. Bond angle is directly proportional to percentage of S character. As bond angle increases, S character increases. As S character increases, electronegativity increases. And we will discuss one example. And one more. Ring size. One more is ring size. Small rings are more electronegative. Small rings are more electronegative than big rings or large rings. Large sized rings. Large sized rings. For example, propane, butane, pentane. More electron withdrawing, less electron withdrawing. So based on the percentage of the character, we can decide whether it is the electron withdrawing group or releasing group based on these factors. For example, I will take this CH3. CH3 is the one, ethane, ethylene, ethyl. So first, based on the hybridization, sp3, sp2, and sp. sp3, sp2, sp based on the hybridization. Next, bond angle 109 degrees 28 minutes, 120 degrees, 180 degrees. Now see here, sp hybridized, more electronegative, more bond angle, more electronegative, right? So like this, we can decide the nature of a group, whether it donates electrons or withdraws electrons, right? Okay, then for example, you have a question like this, same A, B, which is more electro withdrawing group. This is 4-membered. This is 5-membered. Smaller size is more electronegative. More electronegative means minus inductive effect. Obviously, it is plus inductive effect. This is on the ring size. This is on ring size. Next. Right. Next. Generally, what is the use? Why we need to study about this inductive effect? Why we need to study about the inductive effect? Right. I will explain with some example. right? Okay. Among all this, which is more stable? That is a question. Among all this, which is the more stable? Right, see. Generally, see, when you compare between the charged species and neutral species, charged species and neutral species, charged and neutral, sorry. Charged and neutral species, which is more stable? Always the neutral species more stable than the charged species. What is that? If any species with positive charge, it require electrons to get neutral. If any species with negative charge, it ready to donate electrons to become neutral, because neutral is a stable state. That's why it require electrons and it donate electrons. That is, and both are ready to get into neutral state because the neutral state is more stable, right? Okay. And if any species with charge, any species with charge, if the charge is distributed, if the charge is distributed, then that particular charged molecule is said to be stable, because a charged molecules involved in electron distribution automatically either it donate electrons or accept electrons. If it donate electrons or accept electrons, it slowly turns to the neutral state and which is a stable state. If there is no distribution, that is the unstable molecule. Unstable molecule. Right. Coming to this A, B, C, D. This 40 is common for all. Here, the fluorine, chlorine, bromine, iodine is there. Now see here, fluorine withdraws electron from this group. Similarly, chlorine withdraws, bromine withdraws, and iodine withdraws. All can withdraw electrons, right? Okay. But now we need to discuss about the stability, which is more stable, means which readily neutralized. Now see here, fluorine withdraws electrons from the CH2 group, then automatically what happens here, a positive charge will be developed on the carbon. Once the positive charge develops here, the negative charge on oxygen readily involved in the electron distribution. Readily involved in the electron distribution. Once why it is readily involved in the electron distribution, it becomes one to the neutral by providing electrons to this. And the same explanation will be explained for all these cases. Right? Here also same case, here also same case, here also same case. Because all are withdrawing electrons. But at which case? At which case more readily electrons withdraws? In this case, we know that fluorine is more electronegative atom. Therefore, the fluorine can withdraw electron from this carbon more readily. Once it withdraws electron from the carbon, obviously positive charge develops. Once positive charge develops, it readily involved in the electron distribution. So therefore, it readily becomes neutralized and said to be more stable. Said to be more stable. Then followed by this and this and this. So this is depend on the electronegativity of the particular atom. Right, okay, that is fine. Everybody can answer this question because we know the electronegativity of the halogens. Fluorine is more electronegative, we know that too. But if I add one more E, NO2, CH2, COO, among all these five, which is more stable? So far, there is no option E. We can easily decide that as fluorine is more electronegative, it withdraws electrons from the carbon readily. That's why the electron the distribution will also involve readily. Therefore, it is stable because charge distribution, electron distribution takes place, becomes stable. More electron distribution, more stable. Then follows, then follows, then follows. But now I included E. Then how will you decide which is more stable? Right? that can be decided by the electron withdrawing power of a particular group. All these are electron withdrawing groups only. But among all, which is strong electron withdrawing group? That can be given by the classification. That can be given by the classification. For example, I will give the order for the minus inductive effect. Means there are many number of groups from many books. It has been observed that the particular group having the more electronegativity character and the particular group having the higher electronegativity character. Based on that, we have some order of the minus electron inductive effect. Minus inductive effect is nothing but electron withdrawing group. Now I am writing the order. First is NF3 is more stable, then NR3, then NH3, then nitro, then cyano, then aldehyde, then ketone, then acid, then fluorine, then chlorine, then bromine, then iodine, then triple bond, then NH2 equally with phenyl group, and finally hydrogen, which is the reference having the zero minus inductive effect, right? This is considered as the reference. This is the decreasing order of the electron withdrawing power of different functional groups, right? It is having the greater electron withdrawing character. Based on this order, we can decide the stability of any compound. For example, so I included the group 5. If you compare the electron withdrawing power of all these 5 groups, then you will decide which is more stable. See here, we have fluorine, chlorine, bromine, iodine here. Among these halogens, fluorine is more electron withdrawing. That's why when I did not include the E, therefore option A is the correct. But now I included one more option E, which contains the nitro group C, E. The nitro group is more electron withdrawing character than these halogens. Therefore, option E is correct when I included this. Before that, this one, but now because more electronegative character of that group. Similarly, I will give one more example. Same NO2, CH2, COO minus A, B, CH2, CH double one, sorry, CH2 double bond CH, COO minus C, F, CH2, COO minus. So I have three options. Now you can decide this is one functional group, this is other functional group, and this is the other functional group. So come here. The first option is here. Next, comparing these two. Second option is fluorine here. Double bond is at the bottom. Now see here. So after this, I have double bond CH2, then hydrogen, right? Sorry. So among the fluorine is here, double bond is here. Therefore, this is given as the second priority, and finally, this is given as the third priority. Right? Okay. So, which now the give the stability order. A is more stable than C is more stable than the B. So this is about the introduction of the inductive effect. In the next class, we will discuss about the applications of the inductive effect. Okay, thank you. Good night.